This is the Hubblecast, news and images from the NASA ESA Hubble Space Telescope. Travelling through time and space with our host, Dr. J, aka Dr. Joe Liska.
Welcome to the 6th special episode of the Hubblecast, celebrating the International Year of Astronomy in 2009. In the 5th episode, we saw how some telescopes study parts of the universe that we can't see with our eyes. This time, we'll see how telescopes in space have revolutionized almost every field in astronomy. The Hubble Space Telescope. It is by far the most famous telescope in history. And for good reason. Hubble has revolutionized so many fields in astronomy. By modern standards, Hubble's mirror is actually quite small. It only measures about 2.4 meters across. But its location is literally out of this world. High above the blurring effects of the atmosphere, it has an exceptionally sharp view of the universe. And what's more, Hubble can see ultraviolet and near-infrared light. This light just cannot be seen by ground-based telescopes because it is blocked by the atmosphere. Cameras and spectrographs, some as big as a telephone booth, dissect and register the light from distant cosmic shores. Just like any ground-based telescope, Hubble is upgraded from time to time. Spacewalking astronauts carry out servicing missions. Broken parts get refurbished, and older instruments get replaced with newer and state-of-the-art technology. Hubble has become the powerhouse of observational astronomy, and it has transformed our understanding of the cosmos. Hubble is not the only telescope in space. This is NASA's Spitzer Space Telescope, launched in August 2003. In a way, it is Hubble's equivalent for the infrared. Spitzer has a mirror that is only 85 centimeters across. But the telescope is hiding behind a heat shield that protects it from the sun, and its detectors are tucked away in a dewar filled with liquid helium. Here, the detectors are cooled down to just a few degrees above absolute zero, making them very, very sensitive. Spitzer has revealed a dusty universe. Dark, opaque clouds of dust glow in the infrared when heated from within. Shockwaves from galaxy collisions sweep up dust in telltale rings and tidal features, new sites for ubiquitous star formation. Dust is also produced in the aftermath of a star's death. Spitzer found that planetary nebulae and supernova remnants are laden with dust particles, the prerequisite building blocks of future planets. At other infrared wavelengths, Spitzer can also see right through a dust cloud, revealing the stars inside hidden in their dark cores. Finally, the Space Telescope's spectrographs have studied the atmospheres of extrasolar planets, gas giants like Jupiter that race around their parent stars in just a few days. So what about X-rays and gamma rays? Well, They are completely blocked by the Earth's atmosphere, and so without space telescopes, astronomers would be totally blind to these energetic forms of radiation. X-ray and gamma-ray space telescopes reveal the hot, energetic, and violent universe of galaxy clusters, black holes, supernova explosions, and galaxy collisions. They're very hard to build though. Energetic radiation passes right through a conventional mirror. X-rays can only be focused with nested mirror shells made of pure gold. And gamma rays are studied with sophisticated pinhole cameras or stacked scintillators that give off brief flashes of normal light when struck by a gamma ray photon. In the 1990s, NASA operated the Compton Gamma Ray Observatory. At the time, it was the largest and most massive scientific satellite ever launched, a fully fledged physics lab in space. In 2008, Compton was succeeded by GLAST, the Gamma Ray Large Area Space Telescope. It will study everything in the high-energy universe, from dark matter to pulsars. Meanwhile, astronomers have two X-ray telescopes in space. NASA's Chandra X-ray Observatory and ESA's XMM Newton Observatory Hubble, Spitzer, Chandra, XMM Newton and GLAST are all versatile giants. But some space telescopes are much smaller and have much more focused missions. Take Corot for example. This French satellite is devoted to stellar seismology and the study of extrasolar planets. Or NASA's SWIFT satellite, a combined X-ray and gamma-ray observatory designed to unravel the mysteries of gamma-ray bursts. And then there's WMAP, the Wilkinson Microwave Anisotropy Probe. In just over 2 years in space, it had already mapped the cosmic background radiation to unprecedented detail. WMAP gave cosmologists the best view yet of one of the earliest phases of the universe more than 13 billion years ago. Opening up the space frontier has been one of the most exciting developments in the history of the telescope. So what's next? Thank you for joining me in the 6th episode of the special series. Next time, we'll see the new and amazing telescopes of the future that are currently being planned. This is Dr. J, signing off for the Hubblecast. Once again, nature has surprised us beyond our wildest imagination.